Perfect. All right, everyone. So thank you so much for coming. Welcome to another installment of the UQ Philosophy Seminar. And on this occasion, I have the pleasure of introducing Professor Deborah Mayo from Virginia Tech in the US. She is a well-known and prominent philosopher of science, and she was awarded the Lakatos Award at some point in her career. And her work has appeared with all the top publishers in our field, such as Oxford University Press and so on. And today we have the pleasure of having her here in our seminar. It's a little bit late for her. It's midnight, but hopefully things go well. So I'm doubly thankful about that. And she's going to be talking about statistical inference as severe testing. So Deborah, please take it away.
Thank you. Thank you very much. And thank you very much for inviting me to speak at midnight. And are you sure that I should not have my video on?
Yeah, I think it's fine. They're not going to be able to see your video in the recording in any case. I think that this is more stable. Yeah.
Okay. Well, I'm going to be talking about some philosophical controversies in statistics, which I find very fascinating. They're both ancient and up to the minute. They ask one of the deepest, oldest questions about how humans learn about the world in the face of errors and variable data, but they're also the engine behind controversies regarding high-profile failures in the social and behavioral sciences today. And one of the deep questions is, what's the role of probability? Is probability to be used to control the long-run frequencies of error, performance, or is it to assign degrees of belief or support to claims? Okay. Well, the wars between frequentists and Bayesians have been so contentious that everybody wants to think that we are long since past them. After all, we have unifications between subjective and objective Bayesians and frequentists, and people are really interested in whatever works. But the truth is that long-standing battles still simmer below the surface in today's statistical crisis in science, and people don't even agree as to what we might mean about a method working. So what's behind this drumbeat that statistics is in crisis? And by and large, it is that we have powerful methods that make it very easy to find interesting looking patterns in the data, even though they are false or spurious. So I set sail with a minimal principle of evidence, which says that we don't have evidence for a claim if little, if anything, has been done that would have found that claim flawed or false, even if it is. Okay. And in this idea, we need to use probability to assess the error probing capabilities of methods. So that's different from the performance and the probabilist. I view it, as I say here, as a kind of excavation tool. You don't have to accept this notion in order to use it to understand some of the controversies. And in talking about statistical inference as severe testing, I don't mean that we're always testing. In fact, this idea, this requirement for severity holds whether it's a prediction or an estimation or something else that you infer from the data. Okay, so this excavation tool for appraising reforms that we are hearing about every day, and several of them are quite welcome, such as pre-registration and replication checks and avoid cookbook statistics. Others are pretty radical and even lead to violating our minimal. It's very important for people to know in order to subject today's reforms to their own severe critical examination and not just go with what you read, because a lot of it is really pretty wild. And being an outside philosopher can actually help when it comes to combating paradoxical and even self-defeating reforms. Often we would have to take on strong ideological leaders who are very keen to have their favorite methods adopted. And so how do you sift through that, especially with the technical aspects to it? Okay, well, the most often used tools are the ones most criticized. And this is John Ioannidis saying that several methodologists have pointed out that the high rate of non-replication is a consequence of the strategy of claiming conclusive research findings solely on the basis of a single study assessed by statistical significance, a low p-value like 0.05. Well, do people really do that, conclusive research findings on the basis of a single? That's pretty surprising, especially given that the founder of statistical significance tests, R.A. Fisher, had said long ago that we're not interested in an isolated p-value, but rather a reliable method of procedure. And you can't say that a phenomenon is experimentally demonstrated unless you know how to conduct an experiment that would rarely fail to give us a statistically significant result. So you can replicate it. So what are simple statistical significance tests? The Fisherian test is I'm calling a simple test. There's just a single hypothesis. And this is from a paper that I wrote with David Cox. And the goal of these tests is to check the conformity of data with some reference hypothesis. I'm writing it as H0. It can be called a test hypothesis or a null hypothesis. You find a function of the data and the hypothesis called the test statistic. And this test statistic basically tracks the underlying data generating method, such that the larger the value of this statistic, the more inconsistent the data are with H0. And then we can calculate the p-value as the probability of getting a value of the test statistic larger than what you got, under the assumption that the world is similar to what H0 claimed. So we're testing consistency using these methods, and the reasoning is straightforward. If we reach a small p-value, it indicates some underlying discrepancy from H0, because very probably you would have seen a less impressive difference than you did observe were H0 true or approximately true. So it is familiar kinds of reasoning of a falsification variety. Of course, this still isn't evidence of a genuine statistical effect, as we mentioned, Fisher points out, let alone of a scientific conclusion, call that H star, which is going to go beyond merely finding a statistical effect, which is like a first question. So this substantive claim, H star, makes assertions that haven't been probed by the statistical test, and to suppose that it is a classic fallacy of rejection. And this is a very important thing that is not given enough attention, namely how to go from statistical to substantive. But at least statistical accounts should block them. And so now we get to Neyman-Pearson tests that really put Fisherian tests on a much firmer ground by introducing the alternative hypothesis. So you've got H0 and H1, and these two have to exhaust the possibilities. So for example, H0 might say the mean of some distribution is less than or equal to 0, and the alternative that it's greater than 0. The null could also just be mu equals 0, really doesn't make a difference. Okay. So once you have the two hypotheses, you have much more constraints. You have trade-offs between type 1 errors, that's erroneously rejecting the null, and type 2 errors, erroneously failing to reject. And this restricts the inference to the statistical alternatives in the model, so you're not, well, not liable to go off to making substantive inferences. That would be a separate step, kind of a piecemeal approach. Okay, now Neyman-Pearson were so successful in coming up with tests with optimal error probabilities, especially maximizing power, the probability of rejecting the null when you should, that it led to a new paradigm in statistics, which overshadowed Fisher's more informal methods. So even though at first they were all friends, they started to fight, and the fights had more to do with professional disagreements and philosophical ones too, after 1935. But this paradigm of optimality is still very much with us, especially with machine learning and artificial intelligence, because that's the goal usually, to control error. But we still have the ramifications of some of the battles between Fisher and Neyman-Pearson. And I know this group, it says that it involves history, and the history of statistics mixed with the philosophy is really quite fascinating. We often hear that Neyman-Pearson and Fisherian tests are an inconsistent hybrid. This is Gerd Geigerenzer. But the problem with that is that it means Fisher's, or people who follow Fisherian tests, can't use power because that's a Neyman-Pearson notion. And Neyman-Pearson testers can't report the actual p-value observed, but only pre-designated fixed error probabilities. And that's what so much of today's wars have to do with. But actually, both groups used both pre-data error probabilities and post-data attained p-value. In fact, the two accounts, the two programs, are mathematically essentially identical, and they fall under tools for appraising and bounding the probabilities of seriously misleading interpretations of data. And this is Alan Birnbaum. And these are error probabilities, so we can call all these kinds of accounts error statistical. I find that much more apt than frequentist, although it does use frequency probability. It includes confidence intervals, resampling, randomization, and much else that's vital to statistics. And the other great big thing that Fisher and Neyman-Pearson agreed on is how easy and worrisome it is to lie with biasing selection effects, cherry picking, significance seeking, multiple testing. Trying and trying again may practically guarantee an impressive looking effect, even if it's unwarranted. And that's really what's behind today's statistical crisis in science. And of course, doing this will violate the severity requirement, which is why I formulated it. So to give it the full definition, it says we have evidence for a claim just to the extent that the claim has been subjected to and passes a test that would probably have found the claim flawed or false, just if it is. And this probability is the stringency or severity with which the claim has passed the test. So notice probability refers to the method. And severity is really Popper's term, Karl Popper, although he never really fleshed it out. But if you do want to achieve the goal of severity, it requires a third role for probability beyond what the two we usually get. Probabilism, the view that probability is to assign confirmation, support, or belief, such as a Bayesian account. Performance, the probability is to ensure long-run reliability, like coverage probabilities and so on. And typically, only probabilism is thought to be really inferential or evidential. the performance seems, too much of a pragmatic thing that you would do in manufacturing or acceptance sampling. But actually, neither of those is enough to capture the error probing capacity that I'm talking about with severity. Although good long-run performance is a necessary criteria, it's not a sufficient condition for severity. And this is actually a key to solving a central problem for frequentist error statisticians, because often they're asked, well, why should good performance of the tool be relevant for the inference in the case at hand? But ask yourself, what bothers you with selective reporting, cherry picking, somebody who tries and tries again? Here, with this person fishing for a small p-value. It's true that this is going to be very unreliable in the long run, but what bothers us is really about the particular case, that we can't say about the case in hand that he's done a good job of avoiding the well-known sources of misinterpreting data and coming up with claims which then don't replicate when other people use more stringent protocols. So to illustrate these three notions of probability, consider what each says about when a claim is not warranted. Under probabilism, they'd say it's not warranted unless the claim is true or probable or is made comparatively firmer. The performance says it's not warranted unless it stems from a method with good low long-run error. And this third notion, severe testing, which can also be given another P, probabilism, would say a claim isn't warranted unless something, a fair amount, has been done to probe the ways that we can be wrong about C. So I'm suggesting that we want to use probability in inference for probabilism, for severe testing. And this is a distinct notion. Okay. Fishing for significance alters the probative capacity. That's why we have to take account of them. Here's a famous example from the significance test controversy, Morrison and Hankel's book. Suppose 20 sets of differences have been examined and you find just one of them seems large enough to test, and lo and behold, the difference turns out to be significant at the 5% level. Well, the actual level of significance is not 5%, but more like 64%. And so error statisticians would have to adjust their p-values if they want to avoid being fooled by randomness. But this is very controversial. In today's meta research, the idea of having meta research centers is relatively new, but it's not free of philosophy of statistics either. From the Bayesian perspective, the idea of adjusting the measure of evidence is wrong-headed. And this is Stephen Goodman, who's co-director of the Meta Research Innovation Center at Stanford, along with John Ioannidis. He says that these considerations have nothing to do with the data, the fact that you data dredged and all that. Well, for the error statistician, it has a lot to do with the data because it completely changes the capability of the method to probe errors. Okay. The fundamental disagreement here is around this notion called the likelihood principle. In probabilisms, the import of the data is via ratios of likelihoods of hypothesis. Now, likelihoods are often misunderstood, and I don't know how familiar people are here. This would be the probability of the specific data computed under the assumption that H naught is true. That ratio over probability of the data under the assumption that H1 is true. This is the likelihood ratio, okay? The data are fixed. It's the hypothesis that vary. And any hypothesis that perfectly fits the data gets maximal likelihood. So notice that likelihoods cannot follow probability distributions because all rival perfectly fitting hypotheses are going to get maximal likelihood. All right. So, but this principle says all the data are in this ratio. And this notion of the logic of support was first put together by Ian Hacking, who's a philosopher, and he had his law of likelihood that data support hypothesis H0 less well than H1 if H0 is less likely in this technical sense than H1. So it's confusing because in English we use likely also to mean probable. However, he rejected the whole thing soon after, even before philosophers started to take note of his work. And a major reason is you don't have error control. There always is a rival hypothesis, H1, that is going to be more likely than H0, namely one that says things just had to turn out the way they did. And this is George Bernard. Okay. An error probability requires one additional step. So here's the likelihood ratio. But the probability that H0 is less well supported than H1 for some H1 or other is high. Okay, again, this is an error probability, and Neyman-Pearson and Fisher said, we got to look at that. Likelihood ratios are fine, but we need to know how often they lead us astray. Okay. But on the likelihood principle, looking at that extra level of error probabilities is actually to appeal to something irrelevant. And this is Dennis Lindley, a subjective Bayesian, saying that significance levels, power, they all depend on something more than the likelihood function, and therefore something that's irrelevant for Bayesians, namely the sample space, by which he means that once we have the data, it doesn't matter what other outcomes could have occurred. So you can't demand, for example, that hypothesis would very likely have been rejected by some other data. You've got this one piece of data, and that's all you look at according to the likelihood principle. This is the fundamental point of disagreement. If you got this, you'll really understand most of the statistics wars. Now, the weird thing is that some of the familiar reforms today offered as alternatives for significance tests follow the likelihood principle, as I said, standard Bayesian accounts do. So, for example, we hear that the Bayes factor only depends on the actually observed data, not on whether they've been collected from an experiment that has involved data dredging or optional stopping. And this actually a recent paper that I'm responding to here, but an older remark from Berger and Walport, who wrote a book called The Likelihood Principle, is it seems strange that frequentists can't analyze data if they don't know, for example, the plan for stopping data collection. Don't data speak for itself? They ask, and well, the answer is no, at least not for an error statistician. And we can see the effect of repeated statistical significance tests. Okay, this is another kind of multiplicity. Imagine that you have your first sample and you don't find statistical significance, take 10 more, still not significant, take 10 more, and on and on. And the probability of rejecting the null hypothesis with a result that's nominally significant at the 0.05 level, even though H0 is true, increases steadily. This is in testing the mean of a normal distribution, and you can see it very quickly becomes huge. Okay, so this is the problem of optional stopping. And yet for Bayesians, the stopping rule doesn't matter. The fact that it doesn't matter is often called the stopping rule principle. It follows immediately from the likelihood principle. And in the famous paper by Edwards, Linman, and Savage, they say, and if an experimenter uses this procedure of optional stopping, they admit, with probability 1, he will eventually reject any sharp null hypothesis, even though it's true. Still, from their Bayesian standpoint, the stopping rule is irrelevant. And in fact, when they announce this, they're saying, this is wonderful. It really restores the simplicity and freedom to experimental design that had been lost in the cases of Neyman and Pearson and Fisher, because they insisted that you take account of things like optional stopping. So this is a fundamental offshoot of the fundamental disagreement about the likelihood principle. But isn't this weird? I mean, consider this in relation to today's replication researchers. I say they rediscovered that data-dependent hypothesis and data-dependent stopping rules are a major source of failed replication. I say they rediscovered because really everybody knew this already. It was just that in social sciences especially, people were using these data-dependent methods and they thought they were okay, apparently. The fraud busters Simmons, Nelson, and Simonson, in fact, place at the top of their list the need to block flexible stopping. And they say authors must decide the rule for stopping sampling before data collection begins and report this and not go on and on. This is hotly debated. In fact, the current Bayesians often echo Edwards, Linman, and Savage exactly. And this is Eric Jean Wanamaker's, or Wagenmaker's, I guess, in psychology, who says if the sampling plan is ignored, the researcher is always able to reject the null hypothesis, even if it's true. Some people think this is like cheating. The feeling is contradicted by a mathematical analysis. Now, this mathematical analysis, however, assumes the likelihood principle. So when you hear something like this, you really should ask, are you assuming the likelihood principle? And see what they say. So we have a kind of replication paradox, as I say. Everybody is so critical of statistical significance tests, they often say, it's too easy to satisfy standard statistical significance thresholds. And you say, then why is it so hard to replicate significance thresholds with pre-registered experiments? This is you. And the statistical significance test critic comes back and says, well, obviously the original studies were guilty of p-hacking, cherry picking, data dredging, QRPs, questionable research practices. And you say, oh, then clearly the replication researchers want methods that pick up on these biasing selection effects. To which the significance test critic says, well, actually, reforms recommend methods with no need to adjust p-values due to multiplicity. Now, that is the situation today with many methods, our researchers. Think about pre-registered reports. We hear about the pre-registration revolution in the social sciences, right? Why are they becoming so popular? And they find that we get replication much more readily if we pre-registered how many hypotheses we're going to test, stopping rule. It's because the appraisal is altered by considering the probability that some hypothesis, some stopping point or a subgroup could have led to a false positive, even if the reasoning is informal. My point is that insofar as we have a pre-registration revolution, and this is a great thing, it's rather odd, isn't it, that some of the methods, Bayesian methods, say that their methods are insensitive to these error probabilities. Now, granted, there are complaints about the fact that there are many ways to correct p-values. It's a research field of its own, how to deal with it, especially today with big data and omics. But the main thing is to have an alert that the reported p-values, the reported error probabilities are invalid. Now, probabilists can come and say, well, look, they can block intuitively unwarranted inferences. Even with counterintuitive, they could just give a high prior probability to a zero effect, and give it high enough, then it will be hard to infer that there is a real effect. And this could work in some cases, but it really doesn't show what researchers had done wrong. The whole thing becomes a battle of believing in the reality of a certain effect. Does that drug work or not? What's really done wrong is the multiplicity. In fact, data-dredged hypothesis, when you look in your data and you find some subgroup that perfectly fits the supposition that your drug is beneficial, it's hard to resist. It becomes very believable, and that's what makes the data-dredged hypothesis so seductive. Moreover, having to add the prior probabilities is an additional source of flexibility. You not only have biasing selection effects, but priors and their meanings can vary quite a lot. Now, most Bayesians, at least in the last decade or 15 years, don't use degrees of belief, certainly not in statistical practice. They call them non-subjective priors or default or reference priors, conventional priors, there's a whole bunch of names. And the idea is that the priors will be prevented from influencing the posteriors. They're data dominant in some sense, but it's very unclear how we're supposed to interpret these. And also from another paper with David Cox, we note that the priors are not even supposed to be considered expressions of uncertainty or degrees of belief. They may not even be probabilities, being improper, i.e. not summing to one. And there's no agreement still on rival systems for coming up with these default non-subjective priors. I think maybe 15 or 20 years ago, they thought there would be agreement by now, and they couldn't find any non-informative priors either. Some of the different systems around, you may have heard of maximum entropy invariance, maximizing the missing information, or matching frequentist. Okay. Now, so we're talking about appealing to a high prior for the null hypothesis to avoid inferring a data-dredged effect. But there are other consequences, not only the flexibility with the prior, but criticisms of p-hackers or data dredgers tend to lose force, because if you're trying to promote an account that downplays error probabilities, then the data dredger can say that, well, you are just discounting my effect by assigning a very high probability that it doesn't exist. And you can always do that. Let me explain. Remember some years ago, Daryl Bem had this article that some people think was the beginning of the replication crisis, where he inferred the subjects do better than chance at predicting the picture they're going to be shown in the future. Oh, he dredged his data and he found that a certain kind of subject with certain characteristics tended to predict that they were going to be shown a certain erotic picture, that they were shown at some point in the future. And Bem admits to data dredging. And the Bayesian critics who come and argue that this just shows psychologists must change the way they analyze their data, they don't fault him for data dredging because their own account does not condemn that. So what do? They have to appeal to a default Bayesian prior, and they say it's just so unbelievable. In this case, it might really be unbelievable, but this is a general solution for them. So Bem actually gets the opportunity to respond to them what is this spike prior? That's when you assign some high prior probability to there being no effect. And BEM responds to them by saying, you can always do this whenever the null hypothesis is sharp, like a point null, such as mu is 0, and the alternative hypothesis has its priors spread out. What happens is it boosts the probability that any data is going to be higher under the null hypothesis. And this could happen even with statistically significant results. With a high enough prior on the null, you kind of discount it. And what BEM is saying that since you can always do that, your criticism of me doesn't hold. And this is known as the Lindley-Jeffreys paradox, or more aptly, the Bayes-Fisher disagreement. Okay. And he's saying that whenever a frequentist has evidence for an effect, it can be contradicted by a misguided Bayesian analysis. So they've just lost their strongest way to criticize what he did. Many of today's significance test debates trace to this Bayes-Fisher disagreement. And what is it? It's that the posterior probability, this is the probability of H naught given X, and notice I use the given bar here, not the semicolon, because Bayesian, can be high even though the p-value is low. So the low p-value is suggesting there's evidence against the null, but the high posterior is suggesting there's evidence for it. And it can go, it can range very widely. When you give this high spike prior to a point null and spread out the rest, even an alpha significant result, that is one with a low p-value, can result in a high posterior probability to the null. It could be 1 minus p or 1 minus alpha, like 0.95, especially with large n. So to them, to the Bayesian, it looks like p-values are exaggerating the evidence because they're getting evidence for the null. But for the significance test, they're balking at saying this low p-value provides no evidence or even evidence for the null hypothesis. So this is a central criticism, and many people say, and this is Roger Berger now, not Jim, saying concentrating the mass on the point null is biasing the prior in favor of the null hypothesis H naught as much as possible. But the movement that you might have heard of for redefining statistical significance, meaning that we should lower the typical threshold from, let's say, 0.05 or 0.01 to 0.005, is based on this. The spike and smear, that corresponds to a high prior to the point null, and then the rest smeared over the alternative. And so we have opposing mega teams on this. It's not that it's problematic to lower the threshold. I don't even think there should be a rigid threshold, but the problem is assuming that there should be agreement between quantities measuring completely different things. And this is part of a group paper with all of these authors here saying that whether p-values are exaggerating evidence depends on philosophy of statistics. It's based on comparing p-values against quantities like Bayes factors that play a central role in a very different approach with different goals. So this is what the disputes are about. And to see what the formal Bayes factor is, it's just that likelihood ratio piece. Okay, and this is supposed to be the posterior odds ratio. And this piece is where the data come in. This is the likelihood principle in action. This is the part that's going to make the difference for the posteriors. Now, this paper I'm actually writing a response to it by Van Dongen, Sprenger, and Wanamaker, say that, yes, it's true, as Mayo says, the Bayes factor is completely insensitive to error probabilities, but there's a sense in which they say Bayesians can satisfy this severity idea, whether or not the test has been conducted in a severe or less severe fashion, which sounds very puzzling. Obviously, they have a different notion of severity than error control, otherwise they're contradicting themselves. And what they mean is that data can still be much more probable on one hypothesis, H1, than on another. In other words, the Bayes factor can be high. And they sometimes call this a strong test. But a strong test in their comparative subjective Bayesian sense doesn't mean it was well probed. That's the problem. And I call this the fallacy of non-exhaustive contrastivism, because when you're out to form a Bayes factor, the two hypotheses don't have to exhaust all the possibilities. And the fallacy is taking the data as if it supplies good evidence for H1 simply because a non-exhaustive alternative, H0, is falsified or much less likely than H0. Well, you can see very quickly by means of their own example where a white swan is taken as strong evidence for the claim that 90% of swans are white. Well, clearly, this data on a white swan does falsify a claim that all swans are black, right? So if you formed this Bayes factor, you would have 0. You'd have to put this in the numerator, otherwise it wouldn't be defined, right? Because this one has been falsified. But that doesn't mean that H1, 90% of swans are white, has been well tested. In fact, you've done a very poor job in ruling out the ways H1 can be false by just looking at a single white swan. This is a fundamental problem for the Bayes factor in comparison to severity, because in order for H1 to pass severely, there has to be grounds to rule out H1's denial, and you might not get that. Okay, I thought I might mention that the Bayes factor proponents and severe testers do agree we're on the same side against recent declarations that we shouldn't use thresholds and we shouldn't use significance. And I don't know if you're aware of it, but I thought I'd bring it to your attention when the executive director of the American Statistical Association decided that, I don't know, people misuse the notion so much that we shouldn't use the term, but others at the American Statistical Association was quite upset, and the American Statistical Association president formed a new task force that said, no, we shouldn't be banning the notion of statistical significance because p-values and significance testing are important tools that should not be abandoned. And so this is a controversy of its own. Maybe it will come up in the discussion. I want to be clear that I'm very sympathetic to moving away from rigid accept reject rules. With severity, we'll formulate many different severity assessments rather than a binary cutoff. And I was going to show you that if you have time, whatever, the severity reformulation of tests, I'll just do so very quickly, where we're going to evaluate severity in relation to the test, data, and inference claim. And in a nutshell, you test several discrepancies from a test or null hypothesis and infer those that are well or poorly warranted. And I have worked on this over the years with other people, Arispanos, David Hant, and David Cox. And I'll just give a very quick example for how you would compute it. This is mu less than 0, mu greater than 0. Well, typically, if the sample mean is 2 standard errors greater than 0, the result yields a p-value, a low p-value of around 0.02. That's because the probability of getting a mean greater than or equal to 2 standard errors is only 0.02 if you're in a world where H0 is true. That's how you compute the p-value. I'm not sure people how familiar. And so if we imagine the standard error is 1, then observing 2 is yielding a p-value 0.02. And here's the reasoning for inferring the alternative with severity. The observed mean accords with the alternative H1. It's in the rejection region, right? It's a statistically significant result. The probability of the sample mean being less than 2, if we're in a world where H0 is true, is very high. So we at least have an indication of evidence for H1. It's a rather weak claim. It doesn't say anything about how big it is. It just says there's evidence for some real effect. But we would like to go beyond that, and that's where severity comes in. So here we show that you want to avoid misinterpreting low p-values to thinking that you have evidence for a large effect. So we have 0.98, that's right, 1 minus the p-value there. That allows you to say you have good evidence that mu is greater than 0. When it comes to mu greater than 1, the severity goes down to 0.84. And for mu greater than 2, it goes down to 0.5. Again, we're doing this one-sided test here. So this contribution is to avoid misinterpreting the low p-values. The severity is different from power. Some people get confused about that. Here it is, severity going down for the further away that we get when we make this inference that mu is greater than mu1, but the power is going up. So it's the same way that severity avoids what we call the large N problem. And this is back to the Jeffreys-Lindley paradox. If you fix the p-value and increase the sample size, the cutoff, the threshold for rejection gets smaller and smaller. And that's one thing. Some people say, well, lower the p-value if you have large sample size. But severity will tell us that at least interpret them correctly, that an alpha significant difference indicates less of a discrepancy from the null if it results from the larger sample size rather than the smaller. People often get this backwards, but ask yourself, what's more indicative of a large effect? Let's say a fire. If we imagine a fire alarm that goes off with different sensitivities, imagine one that goes off with burnt toast, compare that with one that doesn't go off unless the house is fully ablaze. Well, I like to get an answer from the audience, but without feedback, I'll just say that it is the larger sample size is like the one that goes off with burnt toast. So it's actually less indicative of a serious fire than if it was achieved with a smaller sample size. Of course, you have to have a big enough sample size to test the assumptions. So this comes out very clearly with severity. And very quickly, I'll just say something about fallacies of non-significant results, because that's gotten so much attention recently. If you fail to reach a significant result, it doesn't mean we have evidence of zero discrepancy, but it does allow you to rule out discrepancies that probably would have resulted in larger differences and thereby set upper bounds to how far a discrepancy is warranted. So they're not uninformative the way they're often accused of being. even though it's true, no evidence against is not evidence for. But we can set upper bounds for claims of form mu greater than mu1 in this way. You see it goes in opposite direction from before. Okay, so I don't know if very quick overview. I began with a simple tool, the minimal requirement for evidence, that we have evidence for a claim to the extent it has been subjected to and passes a test. It probably would have failed if it's false. Biasing selection effects make it easy to find impressive looking effects erroneously. They alter a method's error probing capacities, but they don't alter evidence under the likelihood principle. And these are held, this is held in traditional probabilism, such as Bayesian accounts. To the severe tester, the probabilist is robbed from a main way to block spurious results that is so much underlying replication problems. Probabilists may say we blocked inferences without appeal to error probabilities by giving this high prior or spike prior to the null hypothesis. We can still get a high posterior probability for H naught. But the problems is the increased flexibility, and it seems to put the blame in the wrong place. Moreover, we don't really know how to interpret them. The aim of severe testing directs this reinterpretation of significance tests and other error statistical methods to avoid fallacies and to use them more generally in science. Now, I didn't say anything about the other levels in which severe probing, whether formal or informal, has to take place, all the way from data collection to data modeling to statistical hypothesis and substantive claims. But I will admit that one is not always in the realm of severe testing, and a silver lining to distinguishing highly probable and highly probed claims is you can use different methods for different contexts. Okay, so thank you very much for listening, and I'd be glad to take questions. I had said that I would also post a copy of the book